Okay, I think we are good to go here. I know people might trickle in, so very good, guys. So this is the second day. Thank you for joining us. What I'm going to do is I'm going to do a very quick recap of what we have done. Give me 1 second to bring my screen up. All right. All right, so what did we cover yesterday? We looked at a lot of the fundamental concept of AI. We looked at a lot of use cases. I'll do a recap right here. So day one, a lot of use cases. So, things like Uber, right? Airbnb, Bank of America, Chase, all these guys. So the reason is I sort of lead with the use case is so you can sort of see what people are doing, and also it'll give you some ideas. Like, in the previous sessions, when you go through use cases, I had people going, oh, cool, we have something very similar to this use case, right? So it kind of gives you some ideas, get you thinking a little bit, right? So that's great. So we did a lot of use cases. And we sort of looked at, sort of the AI, sort of the overall sort of the AI impact, so some of the markets, AI is going to affect a lot, right? And all that. So we looked at some of the use cases and, and more detail. And by the way, when you guys look at your PDF, you should see like a link for each of the use cases that has more details, right? So I only have sort of highlights in the slides. So if you really want to sort of see, how they did this, please kind of, follow through the link. Yep, so just that. All right. And then we started with some definitions of when you say AI, what do we mean by this, right? So we went through some definitions. I showed you guys some sort of the before and after. So for example, things like what is AI, right? And then also AI evolution. So we looked at things like, so for example, if you do spam detection, we used to write like a lot of rule-based engines, but now those can very easily and very effectively can be done in using AI. So how do we do in AI? Just to kind of recap, we don't write these rules anymore, right? Instead what we could do is we can bring an AI algorithm and show the algorithm data. So spam is a great example. I can say, all right, Mr. Algorithm, here's a bunch of spam emails, and here's a bunch of good emails. So the algorithm will actually go and read through each email message and sort of start learning and picking up patterns of what makes a spam, what makes an email, right? So as we saw, like more data you feed, the better the algorithm gets. So kind of what's happening internally is, internally algorithm scanning, and it is coming up with the rules, right? It's kind of figuring out, oh, okay, if I see this in the email text, that's more likely spam. If I see this, it's more likely a good email, right? So it's actually coming up with the rules, but as opposed to humans writing it, algorithms, they can write rules much quicker, and they could come up with like, easily millions of rules, right? So as each email, each sample is reading, it's kind of, either kind of, tweaking the rules a little bit. So more data, the better, right? And then when the algorithm is ready, you can give it a new email and say, what do you think? This is spam or not, right? It'll classify them into spam or not. So this is a very classic machine learning approach. And again, guys, feel free to ask questions anytime. So this is what machine learning is different. And when I teach this course, I teach a hands-on version of this course for software engineers. And I tell them, this is why you need to learn AI, right? Because if your job is basically writing rules right now, pretty soon that's going to be replaced by AI, right? So you need to be sort of proficient, and you need to learn to use how to do this, right? Or otherwise, your job is going to be replaced, right? So it's because AI is changing a lot of these sort of a software development type of tasks already. And here's an example of how is AI different from a rule-based system, because in a rule-based system, rules are hard-coded. Like, well, somebody has to go and write the rules. And only a programmer can update the rule, right? And analyze a programmer. But in the AI system, the decisions are kind of fed back to the AI system, so it kind of keeps learning. So even if there's let's say I use the mortgage application example, even if it cannot make a decision, it's borderline, it flags a human should kind of make the final decision. Once the decision is done, that decision is then fed back to the algorithm, and the algorithm learns from it. So this is basically called human in the loop, right? So humans So what will happen is, imagine this scenario when I deploy the application, maybe it can only make 50% of the decisions. Other 50% decision, it is kind of borderline, so it will flag the applications, and the humans will review it. So when you deploy the algorithm initially, maybe algorithm can only catch 50% of the applications. The rest, we have to have humans. But as it's learning, its accuracy will improve. So so now algorithm can able to from 50%, it can maybe start growing to 60, 70, 80%, right? And it will keep improving as you can put it through its paces. And that's the beauty of AI, right? AI can continuously learn and get better as it gets exposed to more and more data. And this is kind of one of the things that really distinguishes from like a rule-based engines, right? So hopefully that made sense. So that's how AI is different from rule-based systems. All right. So we kind of looked at a little bit of history of AI here. Again, just more of your reference. So again, we thought, so how the early ideas, like, you didn't write this big, massive program, right? But then we realized, that's a huge undertaking. It wasn't very successful. Then the idea is kind of show the machines the data and let them pick the patterns, right? Just like, how you sort of, the example I use, like how kids learn to talk, right? It's like they just pick up from examples. So all the success stories we hear are due to what we call this bottom-up learning, meaning learning from data. Yeah. So, and today we are going to look at a little bit more deep dive into data, right? So, and I showed you some approach like, Google Translate, right? Because they train on massive amount of data. Now the translation algorithm is much more accurate than what it used to be. And another huge advance we made is image recognition. Again, same thing, right? I mean, so when I look at image recognition, kind of, remember the way I look at it is like, if you have kids, when they were little, you had those little flashcards training them, apple, cat, dog, right? Same thing, right? What we're doing is we are showing the computer like flashcards that says, oh, this is a cat, this is a dog, this is an apple, right? So the computer kind of picks up the pattern, and these initial images, they have what we call label, right? So it says, yeah, this is a cat. And that's a training phase, right? So as an algorithm learning, it says, okay, if I see this picture, this is a cat. Once the training is done, then we show them just a picture with no label. See, it's like there's no label. Now the computer has to guess what the picture is. So, right? So the two-step process. All right. So again, these algorithms, we made tremendous progress. The reason is there are a lot of things that kind of came together in the last 10 years, right? So I sort of, with like history, kind of, just as you can see, just around 2010 is when the current wave started kicking up, and we are sort of riding the current wave. It's about just 10 years old. So what made the big difference? Big data. And we have a lot of tools to handle big data right now. Things like, we talked about, like Hadoop, Spark. These are technologies that are specifically built for big data. And cloud platforms, we call them big compute, meaning, pretty much, as long as you can swipe your credit card, you can pretty much have access to unlimited compute power, right? And we saw how the hardware is involved quite a bit, and also algorithms involved, and also, and this I cannot stress this enough, the availability of open source models. I'll go through this very quickly. So hardware, we sort of say, right? I mean, we know GPU is the go-to platform these days because the way they architect, because their cores, like the individual units, you can cram, hundreds or thousands in a single chip. And GPUs are really good at math, and that's basically what AI is, right? A lot of number crunching. So they've been pretty much go-to platform. for all the high, high end AI work. And now companies are creating their own chips. So we talked about Google's TPU, right? So so pretty much anytime you use Google, like upload a photo or talk to Google Assistant, you're being processed by TPU. Again, what is a TPU? Custom built chip. And there's a bit of a race going on, right? Companies are trying to build their own custom chips. And a lot of the companies like Amazon, Facebook, Apple, they are hiring chip designers like crazy, right? Because they want to build AI chips. So, right. So we talked about, and another thing we saw is like pre-trained model. This is very important, right? Because you're kind of using somebody else's work. And so what happens is these companies spend maybe months or years building these high quality models. And a lot of the times they enter competitions. Like for example, there's a yearly competition on say image recognition, right? So who can do better? So it's a bit of like a showcase for companies too, right? They want to show off their AI their team. So they will run the algorithms, and usually when they submit the algorithm, they also open source the algorithm. So these are great. So they may have spent like 6 months tweaking and fine tuning the model, and now it's open source. So everyone can benefit from their work. So yeah, so and this is like I said, to me like this is sort of the like very practical and very high impact reason AI is going really well, because we don't have to start from scratch anymore. Right? So, and I'll talk a little bit about this today as well. Okay, so, and then so these are basically called model zoos. Basically, what it means, like these where people publish their model. So, all right, and so just to kind of compare GPUs and CPUs, and I thought this is a nice video also. Sort of show this to you guys. If you guys like Mythbusters, this is a fun video.
CPU might do it as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10, 9,
8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
So anyway, I thought, yeah, I couldn't have said this any better, right? So yeah, and I don't know if you guys noticed this, like in their machine, like they have like an NVIDIA logo. So I'm sure, like I'm sure this is commissioned by NVIDIA, right? So you can sort of see, yeah, somewhere like there we go, right? So you sort of see the NVIDIA logo here. So anyway, it's kind of a nice. I mean, I love these guys' show, Mythbusters. Have you guys seen their shows, right? So let me see. Hold on one second. A few people in the waiting room. Yep. So yeah, so these guys do the show Mythbusters, right? And I love their shows. Anyway, so I think NVIDIA can commission them to do like a little demo. Okay, hey, again, you can sort of see the initial version, sort of the right?
CPU might do it as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up.
Let me kill the sound a little bit, and then yeah, so it's like GPUs, since they have so many parallel cores, right? It's like you can sort of see the how insanely fast this is. Yeah. Anywho, so yeah, so I thought this is one of the really great demos, and yeah, I think NVIDIA's money is well spent. This one, so it's pretty cool, right? So that's why we looked at so when I say processing with GPUs, right? I mean, it really does make a difference. I'll tell you an example. Right now, we are working on a project using just a CPU. We are doing some training that will have taken like 2 days. Then we switch to GPU. It's kind of it's kind of done in about 40 minutes, like less than an hour, right? So I mean, that's a huge difference in runtime. Yeah. Anyway, so I thought that was a fun video to watch. And by the way, you have all these links in the video. Let me kind of turn the screen back because sometimes if you share the video, it kind of makes the screen a little fuzzy. Good, guys. So videos, we talked about them. I'll play a few more videos today, just to make them a little fun and interesting. So then we went to the AI vocabulary. So what we did was start learning things like, okay, what is a generic AI? What is a narrow AI, right? Again, the advances we are making right now are narrow AI, right? So, and then we looked at what is AI and machine learning. I mean, PowerPoint notwithstanding, this is how we look at this, right? AI is more like a generic term, right? More like an umbrella term. Machine learning is a sort of a subset of that, very specialized. Basically, works on based on mathematical and stats models. Deep learning employs a technique called neural networks, which kind of still uses that very advanced math, but can adapt to very complex problems, right? So a lot of the problems that we were not able to solve with machine learning are now being solved with deep learning, right? So things like like image recognition, right? When I show a picture, recognize the image as a sort of a cat, a dog, or a house. That was kind of hard to do with machine learning. We really didn't get good results until deep learning came along, and so the deep learning was so good at this, it basically blew all the previous models out of water, right? So things like self-driving cars and language translation, they were only possible because of the deep learning, right? Because it kind of really kicks it up a notch. So, and we sort of saw what how do the deep learning models work? I show the animation. You can sort of see here, right? Let me pull this up again. So basically, what happens is, right? So deep learning is you will see a lot of circles. Basically, each of these circle is just mathematical function, right? That's it. It's a very complex mathematical functions. What they do is the functions are arranged in a certain way. So that's why the whole thing is called a network, right? And these individual things sometimes are called neurons, right? Neurons like a brain. Our brain neurons in our brain. Just inputs go in. Some complex mathematical function is applied, and then output comes out. And they're all in order in a certain way. So here we can see, I'm showing a picture of a cat. So they're looking at the picture of the cat, and the signal is kind of traveling forward. And they're kind of all doing their computations and passing the result to the next layer, and so on and so forth. And the goal is to have them predict cat. But it's right now it says, I'm predicting dog. So I'm saying, no, that's not right. Go back and kind of adjust your settings, right? So it's like, imagine like you're taking a video, right? We're recording a video, like you should as you start taking the video, and you realize, oh, it's too dark, right? You should go and sort of, tweak the settings a little bit. Then you come back and say, oh, this is a little too blurry. It's not in focus. Just sing it, right? So same thing. So that's exactly what I'm doing. So I'm sending the picture, and then also I'm providing feedback, and then say, okay, no, this is right. You got it wrong. Go back. So the beauty of this whole thing and the approach it works is, it used to be people had to hand tweak these mathematical functions, and that was very laborious and and it's very intensive. So we didn't make much progress. But the invention in the last 10 years is basically we figured out mechanisms. The network is smart enough to self-adjust or self-tune. All we need to do is just show it enough data. So as sort of the data goes through and feedback comes back, the network will go back and forth and kind of fine-tune itself so it can predict the correct result. And that's kind of what made possible, right? Because now we don't have to do it, hand assemble these networks. We can just throw computer power into and say here, train for next, you can train for like next 20 hours or, next 2 weeks, whatever, how long it takes, and tweak the network. And that's what happens now, right? So we let the network, pump enough data to the network, and the network basically sort of self-tweaks itself. And it can do, and we are seeing amazing results with this. But at the end of the day, right, I mean, the basic principle is the same. Each of the little blocks is a mathematical function. So that kind of makes sense. So this is kind of where we sort of, because it's important to understand, because sometimes when you see people this neural network, they just like circles, like what do they mean, right? Nothing much, just math functions. Very good. So that's called neural networks. And so again, we talked about training versus inference. So what is training? Training is basically you take an algorithm and then pump data through the algorithm, and the algorithm creates a model. And this, as we know, this is sort of a very laborious process, right? This takes a lot of compute power. Can I give you an example, right? Just to give you an idea, this is where people are building clusters and, paying for faster and faster GPUs because, this is very intensive. And this is always done in the backgrounds, right? Behind the scenes. So, this is a Google Translate. You can see it's working on huge amounts of data. Once the model is ready, inference is very quick. As in, like, you push a new data in, it'll immediately say yes, right? Is it like spam or not spam? For example, like cat or a dog. Prediction is always quick because it has to be, right? So training is always done beforehand, and the models are ready online. So when a new data comes in, they go to the model right away, and the model will predict. Good. And then we looked at a little bit of the, how data size and model size. So, like, just to give you an example, let's say I'm training a huge model to do face recognition on huge amounts of data. My training took a few days, right? But the model size at the end, the model size is pretty small. That can fit on like an iPhone or an edge device, right? So that's how it's done. So I mean, we are kind of spending time passing, because a lot of data kind of passes through, like picture this, right? Imagine these all data kind of passing through. The network is kind of fine tuning itself, and at the end, all I really care is this network. Just the final mathematical function that's basically is going to do my work for me. That's it. That's that. So data size can be pretty huge, but the model sizes are comparatively pretty small. And don't get me wrong. I mean, a 100 meg, 200 meg model sizes, the model is still pretty complex, right? Just sort of the sheer mathematical complex, but compared to the actual data, they are pretty tiny. Okay. So that's where we left it, right? So an algorithm as a model was like, basically algorithm is like a generic formula. You take the algorithm, train the algorithm, then you get a model. So the formula is this, right? Algorithm plus data gives you model. And the model is where we deploy. Model is like, where everything is figured out, right? So that's it. And a lot of the time, people use them, and I use them too, interchangeably. Algorithm, model, I say algorithm, I say model, but yeah, right? But subtle difference. Algorithm is more generic. Model is what we really want, right? So, all right, guys. Any question from yesterday? Kind of a quick review. So we're going to continue on this one today. So here's a link for the document we have been using. So I'll put this in Zoom. So if you guys could come to this place. And if you look in the class folder, I have uploaded slides for today. So here's the slide number 2, right? Okay, so you can download the PDF. I'm sort of, today's, the slides, we have pretty extensive slides. We won't have time to go over them. So I'm going to leave a lot of them as a reference for you guys. I'm going to cover some of these in part 2, right? So, because I always believe in sort of, I like to give you guys more than what we cover. So, you have something extra to sort of to as a reference. Good. So is everybody able to get the slides? So again, once you come here, go to the class folder, right? You guys are here, and then just download part 2 slides, right? That's it. Also, guys, another thing is from here, if you go to the Q&A doc, you can add your questions here. And then also, if you want to network with the with everyone here, so just put your name and contact info. It's always a great way to kind of connect with other people. I highly recommend that. Good, guys. We're gonna get started. Any questions from yesterday? All right, guys. So I'm gonna have you guys on mute just so the line is clear. And then if you need to speak, please unmute and speak, or you can always type in the chat window as well. All right. So today we are going to look at a little bit more in-depth data and machine learning. I'll come back to this video in a second, right? Actually, yeah, let me just actually start with this video. And when I play the video, hopefully you can see the, hear the sound. If not, I'll go through and explain this as well as we go along. So this is a nice video from Google. They sort of talk about what is machine learning and how do we do machine learning. So let's go through this one, and I will explain some of the concepts. Full screen, let's see.
Music, words, spreadsheets, videos, and it doesn't look like it's going to slow down anytime soon. Machine learning brings the promise of deriving meaning from all of that data. Arthur C. Clarke famously once said, "Any sufficiently advanced technology is indistinguishable from magic." I've found machine learning not to be magic, but rather tools and technology that you can utilize to answer questions with your data. This is Cloud AI Adventures. My name is Yufeng Guo, and each episode we will be exploring the art, science, and tools of machine learning. Along the way, we'll see just how easy it is to create amazing experiences and yield valuable insights. The value of machine learning is only just beginning to show itself. There's a lot of data in the world today, generated not only by people, but also by computers, phones, and other devices. This will only continue to grow in the years to come. Traditionally, humans have analyzed data and adapted systems to the changes in data patterns. However, as the volume of data surpasses the ability for humans to make sense of it and manually write those rules, we will turn increasingly to automated systems that can learn from the data, and importantly, the changes in data, to adapt to a shifting landscape. We see machine learning all around us in the products we use today. However, it isn't always apparent that machine learning is behind it all. While things like tagging objects and people inside of photos are clearly machine learning at play, it may not be immediately apparent that recommending the next video to watch is also powered by machine learning. Of course, perhaps the biggest example of all is Google Search. Every time you use Google Search, you're using a system that has many machine learning systems at its core, from understanding the text of your query to adjusting the results based on your personal interests, such as knowing which results to show you first when searching for Java, depending on whether you're a coffee expert or a developer. Perhaps you're both. Today, machine learning's immediate applications are already quite wide-ranging, including image recognition, fraud detection, and recommendation systems, as well as text and speech systems too. These powerful capabilities can be applied to a wide range of fields, from diabetic retinopathy and skin cancer detection to retail, and of course, transportation in the form of self-parking and self-driving vehicles. It wasn't that long ago that when a company or product had machine learning in its offerings, it was considered novel. Now, every company is pivoting to use machine learning in their products in some way. It's rapidly becoming, well, an expected feature. Just as we expect companies to have a website that works on your mobile device or perhaps an app, the day will soon come when it will be expected that our technology will be personalized, insightful, and self-correcting. As we use machine learning to make human tasks better, faster, and easier than before, we can also look further into the future when machine learning can help us do tasks that we never could have achieved on our own. Thankfully, it's not hard to take advantage of machine learning today. The tooling has gotten quite good. All you need is data, developers, and a willingness to take the plunge. For our purposes, I've shortened the definition of machine learning down to just 5 words. Using data to answer questions. While I wouldn't use such a short answer for an essay prompt on an exam, it serves a useful purpose for us here. In particular, we can split the definition into 2 parts: using data and answer questions. These 2 pieces broadly outline the 2 sides of machine learning, both of them equally important. Using data is what we refer to as training, while answering questions is referred to as making predictions or inference. Now let's drill into those 2 sides briefly for a little bit. Training refers to using our data to inform the creation and fine-tuning of a predictive model. This predictive model can then be used to serve up predictions on previously unseen data and answer those questions. As more data is gathered, the model can be improved over time and new predictive models deployed. As you may have noticed, the key component of this entire process is data. Everything hinges on data. Data is the key to unlocking machine learning, just as much as machine learning is the key to unlocking that hidden insight in data. This was just a high-level overview of machine learning, why it's useful, and some of its applications. Machine learning is a broad field, spanning an entire family of techniques for inferring answers from data. So in future episodes, we'll aim to give you a better sense of what approaches to use for a given data set and question you want to answer, as well as provide the tools for how to accomplish it. And in our
So this was pretty good, right? So kind of, I like to show this video because it kind of goes over a lot of the things we discussed. So for example, so it talks about, why, we are in machine learning. The reason is the data is so much now. So the old way of, writing rules manually to process data, just no longer applicable because, you just cannot keep up with the data. So what we need is basically machines to write the rules, right? So that's where machine learning is, right? Because in machine learning, you show them data, they create the rules, right? So, and then, so let me see what else I want to highlight here. Yeah, this is perfect, right? So using data to answer questions. And that's exactly what it is. So when you say, right? So when you're talking about training, right? So that's basically using data. What we are doing is we are using our data to train our algorithms. Then the algorithms answer question, right? So kind of this is the path we had earlier, right? So what I'm doing here is I'm using data, right, to train a model. And this is our past data. For example, let's say I'm a credit card company. I have some past transaction, like millions of them. Some of them are fraudulent, some of them are good. So I'm passing the data to the model and say, okay, hey, learn from this data. The idea is the model learns enough so it can, when a new transaction comes along, the model can examine the transaction and say, is it a legitimate transaction or a fraud, right? So that's the basic cycle, right? Data, we use the data to train a model, and the model serves predictions, right? Yeah, so I see a question from George. Yeah, that's a great question. Yes. So actually, let me see if I can show you guys an example how inputs from models come. Output. Give me 1 second. Let me bring this up. I think I have an example here. One moment. Yeah, thought I had a diagram here. I just need to find it. Oh, there we go. Right. So right. So here, what I am doing is I am actually showing a picture to a model. So there are 2 models in working here, right? So here I'm showing a picture. So what the first model doing is it's basically identifying objects in the picture, right? Okay, like, okay, there's a public plaza, there's a man playing accordion, right? So it kind of identifies everything present in the picture. Then what it's doing is it's sending this data to another model that is captioning this picture, right? So so then it says something like, so the caption goes like this, right? man playing accordion in public square. So exactly. So this is a classic example. So let's say I want to capture an image. So first I need to recognize what's all in the image, and then I need to sequence them, right? Right, because I can just say, oh, I see an accordion, I see a man, I see a public square. You would actually order these words in a way it makes sense. So this is called captioning, and this captioning is basically done by sending the data to another network, and that sort of looks at the words and sort of orders them, because now it has ordered the words in a language specific way. So it says, oh yeah, I see a man playing accordion. So the caption is man playing accordion in a public square. Yeah, pretty cool, right? So anyway, yeah, so it's absolutely right. So you can actually send one model's output to other models, and you can sort of keep chaining them, right, to build really complex models. Yeah, yeah. So very good question. Excellent. All right, so here, in this video, and what else I want to show you. So basically, right, so everything starts with data, because you need data to train the model. And, and this is what we are going to look at today. How do we select the data? How do we train the models, right? Because now that we have sort of basic understanding of all the terminology, today we are going to do a little deep dive in how data and machine learning work together, right? Okay. So these are one of the two cores I really love about data. So one of them is that says, more data beats better algorithms. So the idea was you could spend your time coming up with a very clever algorithm that's trained on small amount of data. On the other hand, let's say I'm developing an algorithm. The algorithm is not all that smart, right? It's kind of, just some, average algorithm, but I train the algorithm on a lot of data. And chances are usually, an average algorithm trained on huge amounts of data will beat a smart algorithm that's only trained on small amount of data. I mean, it's kind of unintuitive, right? But it is true. So that's why this code is like more data beats better algorithm, right? It's a very popular code in machine learning. The second part of this is basically it says, oh yeah, it says, oh yeah. By the way, this is these are people who know something about machine learning, right? So Walmart Labs is basically Walmart bought this analytics company here in Mountain View, where Google is located, and they renamed it as Walmart Labs. So they do like a lot of cutting edge research that then goes to actual Walmart company. So Walmart Labs is more of a research division of Walmart, and they do some really cool work in AI, right? And then and this is Peter Norvig, he works at Google. So he says, oh yeah, look, I mean, it's true. More data is better than algorithms, right? But better data is even beats more data. So as in sort of the data, high quality data, right? And that's why there's a race to collect high quality data right now. So like things like whenever we get our mobile phones and they track our location, and when we upload photos, right? All of this I encourage because they get very good quality data from us, right? So anyway, so let's see how data influences machine learning, and this is a big part of it. So imagine I have some housing sales data, right? So we looked at this a little bit yesterday. So let's say bedrooms, bathrooms, size of the house, and then based on these attributes, I'm trying to predict what the sales price would be. So, right? So what the algorithm is going to do is so what I'm going to do is I'm going to supply the algorithm with the past house sales data. Imagine I already have the data for, let's say, last month, and I have all the stats. So I give it to the machine learning algorithm and say, okay, here, go figure this out. Right? Go learn something from the data. And when the algorithm learned, we can give a new data and then say, hey, I have a new house coming on the market, these are, 3-bedroom, 2-bathroom, what should the price be, right? And the algorithm will predict. Because why? Because it actually learned from the past data. And this is a mystery, like a lot of people kind of get caught up. It's like, how does the algorithm know? It's not magical, because it's basically we are showing the algorithm past data for it to learn from. So as the algorithm is kind of looking at the data, it sort of learns, okay, which is more important? Is number of bedrooms more important, or the square footage is more important? And it's kind of making the decision by looking at the data and looking at the final sale price, is figuring it out, right? And then when I show new data and then say, okay, what do you think? What do you think this house is worth? It applies all the rules it learned and then says, yes, I'm going to predict, this house is going to go for like 500,000. So this is kind of what, I mean, I'm sure you guys have used Zillow and, all these services that predict house prices, right? Same thing. Obviously, their model is much more complex, right? I mean, they consider so many more things, right? I mean, here I'm only considering only 3 attributes. So by the way, these are called inputs, right? So that's why you see input 1, input 2, input 3. So let me ask you guys this question. Let's say you are writing a model to predict house prices. What other inputs would you guys use? Kind of, off the top of your head. We already covered the basics, sort of the bedroom, bathroom, house size. Anything else you might consider to kind of, predict house prices? Location, absolutely, right? So, I'm sure you guys heard the phrase location, location, location. Yeah, exactly, right? So so you consider like the zip code. Even more than zip code, you might consider things like, like little neighborhoods, right? Right? And then, yeah, absolutely, like, lot size. Lot is like, what's the lot house is sitting on, right? Very good. School district, exactly, right? Huge factor. And I know this from, right? In my area, there's like a little river dividing 2 sections of my neighborhood, and the house prices are remarkably different. Why? Because one has a better school district, right? And also, like, what kind of a house? Yeah, so I see this, like, you can, what kind of construction is like a new house, like an old house? Is it like a apartment, single house, right? There are so many things, right? And things like amenities, right? Whether it's like a community, there's like a, swimming pool and all, right? Anyway, so you guys get the idea, right? So the more data, excuse me. So everything you guys mentioned, we call them inputs, right? Input to the algorithm. So the more inputs you give to the algorithm, usually it is better. So yeah, I see. Yeah, it's the question from April. Yep, flood zone, and it's kind of funny. Like, I live in California, so we don't usually worry about flooding here. But yeah, there are yes, right. I get that. And my co-founder, he's in Houston, and I think his house is in one of the flood zones. And during the last storm, was it Harvey? I think, right? Harvey was a big storm. Yeah, his house got flooded. Yeah, and he said he never had to think about this, but until the hurricane hit. So anyway, so yeah, so right, so the reason I sort of ask this question is we can immediately recognize the more inputs we supply, the more accurate the model is. And I can guarantee you, like Zillow and everybody who use housing estimate, they use way more inputs than just the basic ones, right? Exactly, right? So the more because these are called factors or inputs. So the more inputs you consider, your model can be very versatile. And of course, your model is going to be more complex, but it's also going to be more accurate, right? So let's say I only have 3 inputs here. So the model is, going to be a pretty simple model. But let's say, somebody like Zillow, they might consider, instead of 3, they might consider like 100 different inputs. So their model is going to be much more complex, right? It'll take a long time to train and all that, but it'll be far more accurate than mine. Yeah. Anyway, so this is the trick of machine learning, guys, right? When you're training, so we kind of got the gist of, yes, as you train, as you push more data, that's great, right? So more data meaning, so let's say, I have housing sales data, I have 1,000 records. That's good. But if I had 10,000 records, that's even better. So what I mean is, like, I'm adding more rows to the data, right? That's good. So this is what, this is the first quote talks about. More data beats better algorithm. Meaning, if you have 1,000 data points, see if you can find 10,000, right? What Peter Novick said was like, okay, that's good. But what I also want is, I don't want just extra data. I also want extra input, right? So don't just give me extra 1,000 records. Give me more inputs, as in, like, school district, crime rate, traffic, public transit, right? So those are all kind of, you can imagine, come as different inputs. Yeah. Let's see. Right. Yeah. So question from Craig, I see that. Yeah. So there's a bit of a, so, and as you can see, right, as you add input, right, you can say, okay, how about, I just add everything I can think of, like location, rainfall, everything. as you can imagine, just like everything in computer science, there's a cost of diminishing return, right? If you just keep piling on inputs, right? Sometimes what starts to happen is some of the inputs can start noise, and the noise can start drowning the signal. So we have to be a little careful there too, right? So we're gonna just pile on everything we can think of. We have to be selective. So we can say, okay, and this is where the data scientists do, right? So let's say they look at housing data. So let's say I have 100 different inputs. So we might think, you know what, we should kind of pile on all 100 because the model will be better. Maybe. Because out of the 100, maybe only 30 or 40 inputs are really meaningful. The rest is just noise, right? So what will happen is, if you just pile on 100, your model might even do worse than sort of picking sort of the top 30 inputs. Now I know your next question is going to be, how do we know the top 30, right? And this is where data scientists are paid the big bucks, right? Because they analyze the data and figure out which of the inputs are important to build the model. And sometimes a bit of a trial and error, right? They try this out, right? And you don't need to guess, and then there are algorithms that will kind of tell you how important this particular column is. They will say, okay, if you add this, so let's say I have a column called, let's say, let me think of something, rainfall, right? I don't know, right? I don't know if that matters. I just picked something random. So you build a model, you add rainfall, and then you notice, okay, if you add the rainfall as an input, the model is actually doing worse because the model is now picking up noise instead of signal. So you would go and say, okay, you know what? We don't want rainfall. That's kind of detrimental. Yeah. So another important thing we learned, right, just now, we don't just pile on everything. We select which inputs to feed the model. And this is a very repetitive process, kind of iterative process. And this is where data scientists and data engineers get paid a lot of money, because you really need to understand the data to kind of realize, which one makes a better model, right? So again, let me go back to the code, right? Better data beats more data, right? So, all right, guys. So I think we did a pretty good answer. Any other questions? Please, please chime in anytime or type them in the chat window, right? So what we're kind of doing is, guys, we are looking at data and how data is going to influence machine learning, right? So, all right. So we got the learning from data part, right? So the past data, my model learns, and when the new data comes in, because remember, when a new house comes on the market, I don't know what the sale price is. So the model will predict, right? So, and this is what real estate agents do. Like, they look at things like comps and everything else to figure out, okay, what should I price this house at, right? We don't want to price it too low. We don't want to price it too high, because, then you're kind of driving away, potential buyers. You kind of want to price just kind of right to, spur interest, right? So we have seen this already, right? So we do the training part. So training is algorithm learning from data, right? It's very completely expensive, right? But the prediction part, once the model is ready, then the prediction is very quick, right? I mean, so right now when you go to Zillow and type in your house, house address, they will give you an estimate right away. Why? Because they already built the model, right? So they're not, and one of the misconceptions I hear for the first time, people learning this, they say, oh, how are they doing the training so quickly? They're not, right? The training must, maybe the Zillow model, takes 2 weeks to train. The training is already done. And now they have the model live online. And if you go to the website and, punch in your house address, you're not doing the training at that point. You are basically, working with the model that's already created. Yeah. So we get that. Yep. Very good, guys. Great question. So the question is, how often do we update the model, right? So imagine the scenario, right? It's kind of, so let me bring like let's see if we can bring the whiteboard up. Yeah, so let's say this is my timeline. My time goes like this, right? So think of like building a website. So let's say, I sort of work on a website, I deploy the website. So let's say this is my version 1 website. So this website is live. So people come into your website, can look at the website, and they can, work on the website, submit forms and things like this. While that is happening, you are kind of busy working on the next website, right? You're kind of, because as you sort of observe how people are using the website. People open bugs. People say, hey, if when I click on this link, it takes too long, or when I click on the link, it's taking me to a different page. So you're kind of working on the website, the second version, and hopefully it's a better version. Then you deploy version 2, right? So now you have version 2 website live. So this is hopefully better than version 1, and then people have your users have better experience. At the same time, you're kind of working on version 3. Same thing, right? Same thing in model building. So what we do is we deploy models, and just like any other software release, these are versioned. So as the model is live, it's collecting data. You're measuring the performance, right? For example, let's say this model is doing like say Zillow, right? They have a model up, and they are predicting prices, but people are saying, hey, you know what? I'm not happy with this price. You're predicting too high or too low, right? So people are kind of giving you feedback on the website, saying, yeah, you're predicting my house price too high. So you're taking all the inputs into consideration while you work on the next version. So now you're sort of tweaking the model a little bit, right? You're saying, okay, maybe our model is kind of being on the being a little more exuberant, it's predicting higher prices. Let's tweak it down. Then into the next version, better, right? So again, people might be giving feedback and say, yeah, now you're too conservative. Same thing, right? So exactly the same thing. So now we understand the process. Now the question is how often, right? Depends. So maybe you only deploy new models like say once a week, right? Right. If you're a bank, you're very conservative. Let's say you are doing a credit card model, you may not update the model for like a few months. Maybe you only update the model every 6 months, right? I worked in an industry. We were serving online ads and tracking their performance. We will update our model every 2 hours, right? Because in online advertising, you cannot wait a day to update a model, right? Because then I'm missing hits, right? So yeah, so this hugely depends on the industry, and also also kind of how serious and how mature your model is. Like if your model is pretty mature, like let's say you're a bank, you're pretty happy with your credit scoring model, you're not going to be messing with it like on a day-to-day basis, right? So you'll update them, pretty conservatively. Yeah. Great question. So does that make sense, guys? Right? So how often do we update the model? Depends, how well the model is doing, and also kind of overall scheme of sort of how conservative we are. So, great question. Good. All right, guys. So we talked about data. So we understand, more data is better, but better data is better, right? So let's talk about, when you talk about data, what do we really mean? So in data, there are kind of two major kinds. One is called structured data. Other one is called unstructured data. So structured data is what most of us are pretty familiar with. Like think like your data is your database, right? Data is in sort of a, in your Excel spreadsheet, right? If you think of structured data, look at the one we just looked at, like my house price data, like neatly organized in columns. I know what each column means. So think like a database or Excel spreadsheet. So structure, right? Data has structure. Now, structured data can also be CSV files. For example, your data may be something like a CSV file, right? And we are pretty familiar with CSV files. When you export Excel spreadsheets or databases, right? So again, we know, okay, first column is the first name, second column is the email. We get that, right? All of them are structured data. Unstructured data, this is what we are getting more and more of these days. And look at your email. Your email is just just a bunch of text, or a Word document. Same thing, right? Bunch of text. There's no like columns, right? It's just a bunch of words. So let's say a customer is giving a feedback, right? You have a feedback form online. When the customer is giving feedback, they're kind of writing in plain text, right? Or if you're a customer's opening ticket, the ticket notes is just plain text. Also, these are just text data. What about binary data? Things like think about your our YouTube videos, right? Our pictures. So pictures is just a bunch of pixels, right? And our videos are just bunch of photos, right? Or you can have audio recordings, right? You may be recording phone calls. So these are all what we call unstructured data. And more, this is the kind of data we are getting in our world, right? Unstructured. And these are kind of difficult to analyze, right? Because structured data, right, it's kind of simpler because we know exactly what what each column means, and there's an order in the data. Unstructured data is a little challenging. Okay, and there's another one called semi-structured. Excuse me. Sorry, semi-structured is basically kind of in between. It has some structure, but also has mixed data. So imagine, so here's I'm using a Twitter API. So when I query the Twitter API, this is the data I get back. So if you look at this thing, so I see user ID, what device they're tweeting from, right? So take a look at this data, and can you guys tell me which of these data is structured and which one of them is not structured? It's a little bit of a mix, right? Can you just take a second, look at this data, and tell me which one is structured and which one is unstructured? That's right. So what you see is, like, for example, user ID is structured, right? Because I know exactly what the user ID should be. Timestamp looks pretty structured, right? But look at the tweet. It's just a random text, right? So this is just plain text, has very little structure. So what I have here is kind of a mixed data, and that's why we talk about semi-structured. Yep. Oh, and then synthetic data is basically, and the lot of definition. So the way I look at it is more like is data we generate. Like, for example, so let's say I want to generate some sample credit card transactions, but I cannot give out my actual transaction. That may violate some laws, or it may be highly sensitive data. So what we do is we generate synthetic data to represent our real world data, right? Exactly. So this way, and this is true for like April mentioned, like a clinical data, right? Which is very very sensitive. There are HIPAA laws. You cannot just share the data. So what you would do is, yeah, right, exactly. You will create synthetic data to kind of mimic the real world data, but without any sensitive bits in it. Yep. And it's very super useful, because especially when you're dealing with like highly sensitive data, and you're collaborating with people, because they may not have clearance, or they may not have the access. So you don't want to give out sensitive data, right? Because you may be violating a lot of rules and laws. So yeah, good question. All right, so again, like a little infographic, right? Now you can sort of see here. You can see, right? Basically, we are living in a data, in a data age, right? And you can see a lot of infographics, how many bytes we're generating, and right, all this stuff. So anyway, so the idea is, we're getting more and more data every day. You can see this, and also you can see the unstructured data is the one that's growing at a very rapid clip, right? When it's unstructured, I'm talking about like tweets, emails, photos, videos, right? Unstructured data. All right. So now that we have data, right, structured and unstructured, how do we deal with AI, right? What kind of data can AI deal with, right? So traditionally, machine learning has been done in structured data. Things like database, your data in your database, data in your Excel spreadsheet. That is fine. We have an algorithm that do this very well. But the unstructured data, when I say unstructured data, I'm talking about sort of the pictures, videos, right? Where are they? Right? This has always been a challenge. Only in the last few years, we made great progress analyzing unstructured data. So, and that's why remember, we talked about advanced in AI. AI can now do pretty good image recognition, and AI can analyze documents very well, right? And all those changes happened in the last few years because the algorithms have, the latest algorithm were invented in the last few years, right? So, and it's mostly thanks to neural networks. Remember neural networks, I showed you guys earlier, a bunch of mathematical functions, right, working together, right? So these neural nets has been proven to be remarkably good at processing unstructured data. So we'll talk about it in a second, right? So here's a kind of like a little historical, right? So if you look at data as an x-axis, and let's say my algorithm performance, on the y-axis, look at the red one. It's basically sort of a traditional machine learning. What happens is After a while, doesn't matter how much data you throw at the algorithm, it kind of saturates. Right? Meaning, you're not going to get much out of this. So this is what we call classical machine learning or traditional machine learning. After a while, it just kind of saturates. But look at deep learning. When I say deep learning, I mean neural networks, right? Look at deep learning. It kind of starts slow, but it scales much better with data. And that's why deep learning is sort of, making a lot of advances now, because the more data you throw at deep learning, right, the better the performance is. Right? So is that going to make sense with this graph, right? So the traditional machine learning kind of plateauing out after a while, but the newer deep learning algorithms scale much better with data. Yeah. All right. So let's sort of put like a little historical perspective here. Right. So here's my data scale at the x-axis, right? Accuracy here, and so the kind of the green line is sort of the traditional machine learning, and then this one is the neural network. And right now, let's say the 80s and 90s. And you look at this, you will immediately see what's going on, right? In the early 80s and 90s, we really didn't have enough data. So the traditional approaches did better. Right? Let me sort of highlight here. So my traditional algorithm did better. Neural networks didn't really do well. Why? Because we just didn't have enough data to train these guys. So now you can sort of imagine what's happening. So now the line is going to start shifting to the right, right? So I shift to the right, meaning like, I'm going to get more data, right? I'm going to get, I have more compute power available, right? As you kind of keep shifting. So where are we? We are kind of here, right? We have enormous amount of data. We have huge compute power. So what happened was, now the neural networks have taken over the traditional machine learning. Right, so look at this diagram. So this is why a lot of the high-end algorithms like computer vision, language algorithms are all neural networks, because why? They can be trained on a massive amount of data, and they get scale better than the traditional machine learning. Is that gonna make sense, guys? Right? Now, having said this, right? A lot of the time, people ask me, should I use neural networks for my machine learning? Answer is not always. Because think about this in a second, right? If you only have data, remember this is if you only have data, large amounts of data, sure, then the neural networks make sense. So if you're here, neural networks going to give you better results. But what if only you have small amount of data? Maybe, let's say this is scenario A, scenario B, right? If you're on scenario A, maybe the traditional machine learning might give you better answers, right? Because traditional machine learning algorithms work very well on sort of small to medium amount of data. But if you have gobs and gobs of data, like in a scenario B, then you should seriously consider deep learning, because deep learning, by the algorithm scale better with data. So as much as I like to sing the praises of deep learning and the neural networks, right? They are not always the answer. And I know that they're sort of the latest craze, but when we consult with our clients, we always ask them, okay, tell me about the data. How much data do you guys have? Right? Because if you're here, I don't recommend you use deep learning, because your performance is not going to be that great. As a matter of fact, one of the projects I'm doing right now, we are going through the exact same problem, because the client started with using deep learning because they kind of read a lot of blogs and they were very excited, and they started deep learning, but their data set is pretty small, so they're not seeing good performance. So they brought us in. So we kind of went and kind of like step back and say, okay, wait, let's kind of step back and see what's going on. And we actually are recommending them to go with the traditional machine learning approach. And already we are seeing a huge improvement in the result. And that's why since you guys are going to be decision makers, right? That's why I'm spending time on this slide here, because this is very important, right? Just because Facebook did some and I see this all the time. People come and say, I read the blog from Facebook. They like solve this problem, right? And I'm like, oh, that's great. That's good for Facebook. But we don't have their data, right? Facebook has probably more data than anybody in the world. Maybe only second to Google, right? Sure. So they can spend the algorithm can do this. But we, on the other hand, we have only small amount of data, right? So we have to kind of choose the algorithm that's best for us, right? Oh, got a question. So question like, what is small, right? Yeah, so this is a great question. Again, it's very subjective. So when it says small, so to me, again, kind of not to put and there's not like a line in the sand on this one. So if you have like, terabytes of data, then I'll kind of consider that as big data. If you have like a few gigs of data, that's small. And as you notice, like there's like a kind of a gap, right? So kind of like a few gigs of data, and we talk about this a little later, and a few terabytes of data. This is kind of big data, right? And this is kind of small data, medium, and there's a lot of space in between, kind of what I call medium data, and yeah, that's kind of subjective. And we will talk about it. I have a slide coming up on this one. We'll talk about this. Right? Good question though. Yeah. All right, guys. So right. So are we clear on this one, right? So again, so we need to be very clear-eyed on figuring out which algorithm we are going to choose, because the latest greatest algorithm from Facebook is not always the answer for us. just say. All right, guys. Any question on this one? Basically, it's data and how the algorithms work. All right. So hopefully this made sense. All right. Let me see what else. The next one. All right. Let me highlight this one here. A lot of the time, because remember, data is the first step of the when you're doing AI. So a lot of the times, what I see is when people say, okay, we should do AI. Okay, for next 1 year, we are going to start collecting data, and then we are going to look at AI. I think that's a wrong approach. What you should do is you should start simultaneously, right? You should start collecting data and also start on AI projects, because not all the data may not be useful. And if you just spend 1 year just collecting data and then bring in an AI team and say, here you go, here's the data, make something out of it, they might say, oh, this data is not very useful, right? And this is a mistake I see in some companies. They say, okay, step 1, data, spend 6 months, 1 year doing that, and then step 2, let's bring on AI team, right? So I always recommend it's a kind of iterative process. You definitely want to involve the AI team early on to say, okay, this is a problem we are going to solve. Tell me what kind of data we need to collect. And as you collect the data, the AI team should be actually building models and experimenting and then figuring out and giving you feedback to say, okay, this is good. I need more of this data. Maybe not so much this, the other data, right? So anyway, so very careful, and especially when you're starting out, right? This is a common mistake I see, right? Spend a lot of time gathering data and then bring on AI just to find out, oops, the data we collected is not all that useful. Okay. All right, good. Right, so let's talk about how to deal with big data. And this is the question you guys ask, like, what is big, right? So here's like a little, little kind of a table, just to kind of, conceptualize some of the data sizes, right? So, for example, let's say you're writing an email. Your size are going to be getting kilobyte, right? So, just so maybe a couple of paragraphs of data. That's it. A photo is a few megabytes in size, right? So if you download a song on Spotify or something, it's like 1 to 5 megabytes. So again, these are pretty, how do you say, pretty imaginable sizes, right? We deal with them on a day-to-day basis. Then you talk about gigabyte. Gigabyte is like, imagine your, like for example, your memory on your phone, right? Let's say my phone has 128 gigabytes of memory, right? And also computers, when you look at memories, computers typically have gigabytes of memory, right? So again, this is the size we encounter on a daily basis. So next step up. So if you take 1,000 of the gigabytes, then you become a terabyte, right? So what is a terabyte? Again, if you look at your computer hard drive, you probably have like a terabyte of hard drive these days, right? So when you're getting in the terabyte size, this is where I kind of say, okay, now we are kind of slowly getting into the big data territory, right? And next step is petabyte, right? I mean, this is a huge amount of data, right? So you can sort of see here, right? So Facebook generates 4 petabytes of data every day. By the way, each of the rows is like 1,000 times than the other one, right? So for example, 1 megabyte is 1,000 kilobytes, and 1 gigabyte is like 1,000 megabytes. So just multiply everything by 1,000, right? So every row you go down, you're like 1,000-fold, right? So terabyte is kind of, I think, for most of us, this is kind of probably the larger data we see, like, our laptop drives are terabytes. That's it. Petabytes, like, I mean, this 1,000 times the petabyte, that's a terabyte, I'm sorry, right? You can sort of see some of the, right? Like, for example, Uber has 100 petabyte data. So if you're here, right, I think if you're, anywhere beyond this, you are definitely in petabyte territory. And I'm not even going to these things, I can't even like fathom what they look like. But yeah, they are like 1,000 times better than the other, right? So I worked with petabytes data before, right? When you do machine, big data systems, we had petabytes of data. That's as far as my exposure, right? So typically, I kind of see here, right? If you're in this area, like a few gigabytes of data, this is kind of, I would say, small data, right? So if you look at like a little spectrum, right? So you're starting at like megabytes, right? Gigabytes and petabyte. Sorry, terabyte. I'm sorry, terabyte, right? So I would say kind of small, medium, large. So think like a T-shirt sizing, right? Yeah, and again, this is very subjective. Like we had clients who would say the most data we are going to ever have is like 10 gigabytes. That's it, right? And they do machine learning just fine. And machine learning has been pretty useful to them. We also had clients who generate like 1 terabyte of data on a daily basis, right? So they are definitely in the big data territory. So again, you can have to like look at that like a little bit of a spectrum to figure out okay where you are, right? So hopefully this table made sense, guys. Yeah. Any question on this one? So question like why do we need more data, right? It's precisely for one second. This reason, right? If you have more data and if you use advanced algorithms, almost always, there are exceptions to this, almost always you get better results, right? I'll show you a video on this one real quick. Yeah. Now remember, yeah, so for example, if you look at like a picture might have millions of pixels, right? Especially, I mean, even the pictures we take on our phones are pretty high quality, right? You're right. So yeah, so the reason Googles and Amazons now give us a free storage for our pictures is why? Because they want to collect all the data and then train the algorithms. So the more data they have, right? As you can see, the algorithm gets slightly better and better and better. Right? That's the name of the game. Right? No, actually, so there are two things here, right? So yeah, I see what you're asking, Anton. It's like you need kind of like this. I sort of look at both. Where are we here? Right? You need more data. You also need better data. Right? Yeah. So a lot of the time we start with more data, meaning just just push data through the algorithms, and then once we have some decent performance, then you can start sort of getting more picky about say, okay, let me sort of pick and choose which inputs I'm going to push in, right? Because some attributes, some inputs are going to yield you better results, right? And it's a bit of an experiment, right? There's nobody can tell you, oh, this is important. The way you find out is by trying it out, evaluating the final model, and say, okay, which if I add this column, does it improve my model, or does it or does it even do worse, right? So it's a trial and error right now. Yeah. So we try a lot of experiments and pick the model that gives us the best combination. All right. So when you have big data, so when I say big data, we sort of see the size, like if you're like terabytes of data. Okay, so the question is, okay, how do we deal with this? And this is where we have big data systems. There are essentially two choices here. You can store the big data on premise, and if that's the case, pretty much the go-to platform is Hadoop, or you can choose to any other cloud vendors. So I'll talk about both of them real quick, right? So let's talk about Hadoop. So you probably heard me mention Hadoop a few times in this course because Hadoop is sort of the first big data platform, right? And is open source. So it has a pretty wide adoption. So the little history is, Yahoo basically developed this in like, 10 years ago? And to their credit, they open sourced it. And since then, it became a pretty sort of the de facto standard for big data. So the reason Hadoop works really well is it's a distributed system. So, like Yahoo at one point ran 5,000 machines, because it's a cluster system. So you can build a Hadoop cluster with 10 machines, or you can see thousands of machines. The Hadoop ecosystem is designed to scale to thousands of machines, right? So you can imagine like a massive, because you know, a massive cluster. And it's very well proven, like a lot of big companies use it, like Twitter, Facebook, everybody uses Hadoop. So Hadoop is very well proven in the field. So you can start small. Let's say you can start with like a 10 node cluster, and then you can scale up to thousands of machines. And the way Hadoop works, you can sort of see here, right? So these are individual machines. They are called worker nodes. So as you can see, there are a few things I want to highlight. Your data is distributed across many machines. We have huge amounts of data. It's not going to fit in one machine. So what we do is we distribute the data across many machines. And also when we run our queries are also distributed. You can sort of see here, right? Our queries are also distributed across many machines. So that's the secret for Hadoop. Everything is distributed. Data is distributed. Also compute is also distributed. Make sense? And by the distributed architecture, they're able to scale to massive scale. So if you're using big data in-house, most likely, right, you're probably using a Hadoop system, because that's sort of the right now de facto platform for big data. And Hadoop can scale better than any database we have seen. And also it costs much less. So here's like a little pricing chart I picked up from one of the Hadoop vendors, right? So on the x-axis, you see the price per terabyte. Right? So if you want to store 1 terabyte of data, how much you are paying, right? So, and they did the comparison. This is a couple of years old, but still relevant. So let's say you're like some SAN drives, from like Hitachi, IBM. They can cost you from, for store 1 terabyte of data, anywhere from, like 30 grand and up, right? And if you have things like Teradata, Oracle, right? They can cost you anywhere from 20,000 and upward, right? And if you look at Hadoop, you can see, how cheap it is, because it's maybe like 2-3 grand per terabyte. How do they achieve this? Because Hadoop actually uses commodity hardware. So Hadoop hardware is just stuff you buy off the shelf, like from Dell or HP, these guys, right? So that since they use commodity hardware and they have very different architecture than databases, that's where they're able to scale to pretty massive scale while keeping the cost down. So right, so you're thinking about storing huge amounts of data. People think, okay, if you have say 100 terabytes of data, and if you have like an Oracle system or like a Teradata system, how much are you going to pay? Right, that's pretty expensive, right? But let's say, okay, if we can use Hadoop, then at least from the storage, you'll be saving a bundle. And the one cheaper than Hadoop is cloud storage, right? And because the reason is because cloud storage is this massive scale, so they kind of get savings at the savings of scale, right? So is that gonna make sense, guys? Kind of Hadoop again, just a very high level overview, right? If you're doing in-house big data, most likely you'd end up with Hadoop, right? Also, another choice, if you don't want to deal with data in-house, you can use cloud vendors, right? I mean, and this is where they make their money, right? If you choose a cloud platform, you can basically upload pretty much unlimited data into the storage, and they basically charge you per usage. So here's kind of when I sort of looked at all three, Amazon, Google, and Azure. So the cost I'm saying is how much it's going to cost you to store 1 terabyte per month. Remember, this is a recurring fee, right? So every month you're going to be paying this. So there are, I can see like $20, right? So for each terabyte you have in the cloud environment, you're going to be paying about $20 a month. So we have 100 terabytes, what are they, like multiplied by 100, maybe around 2,000 a month, right? So this is very convenient because you don't have to maintain any infrastructure. You just upload everything to the cloud. But also you have to understand this cost can add up, right? If you have really large amounts of data, your monthly bill can be pretty huge. So you have to make a call, basically what works for your organization. Do you want to maintain your data in-house, right? So you can use something like on-prem things like Hadoop, right? Teradata, Oracle, these guys, or you can go to cloud. And this calculation is different for everybody, right? I had clients go from on-premise Hadoop to cloud because they didn't want to deal with infrastructure. They just wanted to focus on data, right? I had clients who went from cloud vendors back in house because they realized that their cloud expenses are going through the roof. So yeah, right. So it goes both ways. So again, what's right for you guys? It's going to be it's going to be pretty unique. So only you can evaluate which is the right approach for you guys. Right? But these are choices typically, right? So comparison for Hadoop, there are a bunch of I see a question from Greg. There are a bunch of companies who claim to do like on-premise large-scale storage. These are file system companies. Like one from I used to work for one in Hitachi, right? They did a proprietary file system competing with Hadoop. But honestly, I mean, Hadoop is sort of the de facto standard right now because the beauty of Hadoop is it's open source, and also Hadoop also gives you processing, right? Here's the thing, right? If you just buy one of the file systems, only thing you have is just just a file system to throw your files at. With Hadoop, you get both. You get file storage as a distributed system, and also you can query the files very quickly, right, in a distributed file. So with Hadoop, you get both. So that's why Hadoop sort of beats sort of the traditional large-scale file system, because a lot of the large-scale file systems are just that, just file storage, nothing much. So again, right? So again, because even though Hadoop is kind of, this is what Hadoop is, it may not be the right choice for everyone because Hadoop is kind of, it's a complex system. You have a team of people, managing it and maintaining it. But I worked on a fair number of clusters, Hadoop clusters in my, in my professional career, and it works really well, right? Exactly. So good questions. All right, and so summary is we have big data. How do we store on-premise Hadoop, and there are other file systems, or you can do cloud, right? And cloud system, can basically pay monthly. All right. All right. So very quickly, I'm going to show. So we kind of talked about machine learning versus deep learning in a little bit, right? I shown you the graph already. So right, you guys have seen this animation, so I'll sort of skip through all this. So the way deep learning works, so you guys understand the animation, right? Kind of, layer by layer, these mathematical functions kind of do some work. A little insight into this is, imagine I'm using a deep learning network or neural network to do face recognition or like any image recognition, right? So now you guys already know these are arranged by layer. So like a little deep dive into this. So let's say I'm sending a picture of a face. The first layer, right? So first layer, these mathematical functions are optimized to detect very simple features. Like for example, it'll say, I detect like a, like a vertical line. I detect like a, like a slanted line. That's it. They're recogniting small features. Then what they do is they crunch their numbers and send their result to the second layer, right? Again, same thing, right? So in a layer by layer approach, right? Second layer. The second layer can basically put together results, sort of builds on what the first layer has done, and it can assemble and recognize more complex shapes. So you can see something, it says, oh, I see an eye, right? I see an eye. I see a nose somewhere here, right? I see a nose, right? I see an ear. So what it does is it sort of assembles or builds on top of the layer one's work and recognize more complex shapes. Same thing happens, right? They can do their work and send their result to the third layer. Now the third layer is kind of building on everything the second layer has done and starts recognizing a face. So this is basically how neural networks work. Layer by layer, first few layers, they only recognize like a kind of a low level features. As you go down the layers, these layers are optimized to recognize more sort of complex patterns. Yeah, does that make sense, guys? Yeah, that's it. Right. So that's how a lot of the neural networks work, right? Let me see. I'm going to show you guys a quick video on this one. And so again, we went through all this data, so I'm going to skip over this. I'm going to show you a quick video by Andrew Ng, and then we'll take a quick break. Okay. So let me play this video. And again, same thing. Hopefully you can get the sound.
AI is making amazing progress, and today is already making lives better for hundreds of millions of people. I wanted to create a few videos to share with you some of the latest exciting trends in AI, as well as maybe give a little bit of advice about how you yourself might be able to apply AI or how your organization might be able to do so. In this first video, I want to share with you some thoughts on how scale is driving the latest progress in AI and machine learning, and specifically in deep learning. The latest hottest trend in AI is deep learning, also known as neural networks. I've shown an example of one here where, here you would have some input, such as maybe an image or an email, and then all of these simulated neurons process the input until eventually you get an output here, such as recognizing someone's face or deciding if a piece of email is spam, and so on. So many of the basic ideas in deep learning or in neural networks have been around for many decades, but it's only in the last few years that these ideas have been taking off. Why is that? At the risk of oversimplifying slightly, I want to present one picture that tries to explain the rise of deep learning. There are a lot of reasons behind the recent rise of deep learning, including a lot of great researchers all around the world creating lots of algorithmic and other innovations. But if I had to pick just one idea that I think explains the rise of deep learning the most, then this would be it. So I have here a plot that I'm going to fill in, and on the x-axis I'm going to plot the amount of data that we have for a problem, and on the vertical axis I'm going to plot the performance on some unspecified scale, but so some sense of the performance of how well our algorithm is doing on some task. If you were to use a traditional learning algorithm, such as a support vector machine or logistic regression, then as the amount of data increases, the performance of the learning algorithm might look like this, in which it goes up as you increase the amount of data, but then pretty rapidly, nearly plateaus off. So it's as if, even as you increase the amount of data, the learning algorithm doesn't quite know what to do with the more and more data you might be able to give to it. Well, how about deep learning or a neural network? If you train a small neural network, that is with a relatively small number of simulated neurons, then the performance maybe will look like this, in which, as you increase this amount of data, its performance gets better, but it still plateaus off after a while and doesn't get that much better with more data. But one of the exciting things about neural networks is that if you then train a somewhat larger neural network, maybe then the performance starts to get better and better, even as you increase the amount of data. And so that's maybe how well you do if you train a medium-sized neural network. And if you train a very large neural network, then your performance might look like this, in which the performance just keeps getting better and better as you increase the amount of data. So I think what's happened over the last few decades as humanity spent more and more time on digital devices is that the amount of data we had for a lot of problems increased. So we moved to the right of this curve, and for a lot of problems, not a lot, but for many problems, we're now in a regime of having a lot of data. With the traditional learning algorithms, the performance still wasn't that good, even with a lot of data. But as we build huge neural networks, we find that these neural networks are better able to take advantage of the huge amount of data that we now have access to. And so what we see today is that for many problems, not all, but for many problems, in order to get great performance, you need to first train a very large neural network so that you're on the green curve, and second, make sure that you have a lot of data so you can hit a performance point that's up there. In order to make sure that you can build a large enough neural network and also process a huge amount of data, this is why also a lot of the bleeding edge research in machine learning or deep learning is switching to HPC or high performance computing, in order to have the scale needed to process a huge amounts of data and on very, very large neural networks. So that's it, a single picture that tries to explain how scale is helping to drive the rise of deep learning. And this is of course complemented by a lot of algorithmic innovation, by a lot of amazing researchers as well. Before I wrap up, just to mention, turns out today that one of the most reliable formulas, one of the most reliable ways to get good performance on a machine learning problem is this maybe relatively simple, well, it seems simple but hard to implement, formula of having lots of data and training a huge model. And if you're able to do both of these things, often that's a reliable formula for getting better performance on your task as well. That's it for this video. In the future, I hope
right? So I always love this like a simple formula. It's like, yeah, so it's like basically the success for achieving great performance is like, yeah, just have big data and more data and a bigger model. So kind of like E equal MC squared, right? So yeah, so like, yeah, simple formula, but easy to say in theory, but very hard to do in practice, right? But hopefully this gave you guys a sense of right, where we are, right? So like right now the race is basically building bigger and bigger models and training them with larger and larger data, right? So kind of right, so you kind of outperform everything else. So hopefully this kind of summarizes kind of the data and machine learning. Any question on this one, guys?
To
Very
keep
good.
on creating.
Sorry, stop that. Very good. So again, all these videos, are part of the slide decks, right? I love to show these videos as we go along to make these just just a little bit more and entertaining, right? So, but these are really great videos online. 1 second. Yeah. All right, guys. So let's do this. Maybe we take a quick break, say 5 minutes, and then when we come back, we'll continue. Yeah. So maybe a quick break now, and then we're going to continue. All right, guys. I'll see you guys in about 5 minutes. Okay, guys, so let's get started here. So if you look at the PDF for today, I have quite a few slides. I won't be going through all of them, especially sort of the ones towards the end where I talk about some of the software ecosystem. It's basically some of the libraries and software we use for AI. It's for your reference. You can sort of see some of the right I sort of broke them down into things like what environment, whether you use R or Python, right? What kind of libraries they use, and also frameworks, right? Kind of broken into sections. And the subsequent slides, I sort of talk about, what each of these are, right? So please, so this is more for your reference. I'll skip on this one because I want to sort of talk about some of the process and some of the other AI projects, right? Let me see where we are. So very quickly, we have looked at data and AI. So we understand, right now sort of the race is sort of the bigger and more data, right? And the reason it's going this way is because that's what right, with our current inventions, current technology, this is sort of the reliable way of producing better results, right? You throw more data at the algorithm, and then you keep building bigger and bigger models. So they're performing very well, right? So that's not to say this is the course we are going to be doing in the next 5 or 10 years. Maybe somebody else might come up with a completely innovative algorithm that doesn't need a lot of data, or that does things very differently, right? Who knows, right? So again, this is still we are still sort of discovering new things on a daily basis. But right now, sort of the foolproof approach is grab a lot of data, throw it at the algorithm, build the biggest model you can, and that gives us. It's almost like a brute force approach, right? So we are kind of throwing compute power at this problem. And that's why, like a lot of these companies, like if you look at who is doing really well in AI, sort of the Googles, Facebook, Ubers, they all, they have tons of data, and also they have very good infrastructure to do this work. And also, but please don't let this deter. And when I say this, like some of the people say, oh, we don't have the infrastructure of Uber or Google. But here's the thing, right? When I say AI, we don't have to start with like a self-driving car, right? So that's kind of the really bleeding edge of an AI application. For a lot of us, applying AI could be something like increasing conversions for a customer, right? Or maybe you have some prediction model, learn to predict better, right? And those things you can start with modest amount of data and a lot of standard algorithms. And so sometimes, as much as I enjoy showing you guys these, sort of bleeding edge resources, I kind of, also need to mention, please don't let these, dissuade you from trying AI, right? So AI can be started with like a very small to medium amount of data, and that's what I want to talk about next, all right? Very quickly, I want to talk about some of the common algorithm you will hear, just so just to kind of for your benefit, for your reference. So in AI algorithm, this is a kind of a algorithm summary. So it divided into sections like supervised, unsupervised, and reinforcement learnings. So you will hear people talk about we're using regressions. What is regression? Is basically anytime you want to predict numbers, it's a regression, right? Classification is something like whether you want to predict whether the cell has cancer, or this transaction is fraud, right? Like one or the other, right? You're classifying. And these are some of the popular algorithms. So for example, if somebody says, we are using random forest, right? Right? Okay, this is part of a decision tree algorithm and a supervised. And it's a supervised, what it means is supervised algorithm to learn and then predict, right? So it's more of your reference and say, if somebody says, oh, we are using, SVM, right? You know what it is, like SVM, okay, we get it, like it's a classification algorithm, it's a supervised algorithm, right? So again, I don't want to go too deep into this, but it's more like a reference for you guys, and I'm going to zip over some of them real quick, right? So typically you will hear people say supervised algorithms, unsupervised, and I'll talk about one of the latest inventions called reinforcement learning. So supervised is basically, that's it, right? This is exactly what we learned so far. Algorithm learns from training data and then predicts on new data, right? So let me talk about this a little bit. So, right, we learn from training data and then predict. So things like predicting house prices, predicting credit card fraud, they all kind of fall under supervised methods. Right? We train first, then we predict. Right? So a lot of applications, so for example, predicting stock market data. So what you do is you sort of train on the past stock market data, and then hopefully your model can predict the future stock market, right? So if anybody figures this out, please let me know, right? I want in on this. So, right, so, all right, so that's supervised. Unsupervised is basically, I mean, I'm sort of skipping through some of the slides and some examples, just to kind of, I want to cover a few things as well. Unsupervised, basically, there's no training. Algorithm tries to find patterns in the data. So let me show you an example, it'll make sense. So let's say I show you a picture of, some, a plot of some data. And I see sort of, 3 distinct groups. And if you ask you to say, do you guys see any patterns? You'll say, sure, right? I see 3 distinct groups. Maybe these, these are like, I'm sort of classifying, sorry, I'm sort of, not classifying, I'm sort of, I'm organizing beverages. So since white wine, right, these dots are like sample data. Since they sort of share similar properties, they kind of, cluster together. Beer probably have different properties, so it kind of tends to be its own cluster. Red wine, right, another cluster. So what we are doing is we are kind of looking at the data as a whole and trying to pick up patterns. So the computer science term is clustering, right? You're kind of find clusters of similar data. So example could be something like, it's called anomaly detection. For example, let's say you're analyzing some, fraud data. It could be credit card fraud, or like you're analyzing network traffic. So let's say usually your traffic kind of happens, maybe let me draw here, around this area. But let's say suddenly you sort of start seeing some data outside the usual area, you might think, okay, hey, this might be something abnormal. Need to go investigate. And this is called anomaly detection, right? And it's a very popular use case for clustering, because you're kind of trying to look at the data and finding patterns. That's it, right? So another example I saw is like, for example, another way clustering is, this is a pretty popular case, and you probably have observed this without thinking too much about this. When you guys go through like Walmart or Target, when you walk through an aisle, you see like a little bin, like a center island set up with some items, right? And most of the times the items are kind of unrelated, right? I remember this, I was working through cereal aisle at my local Safeway, and then they had a center aisle basically with like LED light bulbs. So how are they related? How are the cereals and LED light bulbs related? They're not, right? But as it turns out, I needed a few light bulbs, so I ended up buying some anyway. So I kind of started thinking, why did they have this here, right? Why did they have these LED light bulbs in the middle of a cereal aisle? So as it turns out, it's not like a random act. It's actually, they actually segment or cluster your purchases. So this is an experiment from Walmart, and actually you can find this, Walmart actually published their findings. So what Walmart did was they analyzed all the shopping baskets, whether you did online or offline or in store, right? And then they kind of figured out, okay, what kind of trip you made? Did you just come for a quick pharmacy trip? Maybe it's allergy season, you want to pick up some allergy meds, right? Or you just did like a grocery run. Or did you just do like a milk run, right? And you guys probably can guess what this is. So, right? So what they do is they analyze, what you're buying, and they try to sort of guess what kind of a shopping trip it is, right? And based on the data, this tells stores how to put things together. You guys probably heard of, like a popular, it's like a popular tale, how like Target used to stock beer and diaper together, right? So people, when parents come in to buy diaper, they also pick up beer, right? I don't know how true this is, but it's a very popular law, right? And how do they figure out how to sort of put beers and diapers together? Because they look at the purchase patterns and figure out, okay, hey, people who buy diaper also tend to buy beer, or it could be diaper and milk, who knows, right? So, and that's how they organize these things. In an online store, this is easy, right? In an online store, when you buy stuff from Amazon, for example, when you add things to your to your cart, they will recommend things right away, right? Because they don't have to kind of rearrange things like in a physical store, right? So Amazon can quickly update the algorithm. So you can say, let's say I'm buying I'm buying a laptop. They can quickly start recommending things like extra disk or laptop bag, things like this, because based on what they have seen before, Anyway, right? So this is called clustering. So clustering basically meaning identifying patterns. So these are some of the popular algorithms you will encounter. So if somebody says, oh, we are using clustering algorithm, now we know what it is, right? It's basically trying to find patterns in the data. So if somebody tells you, oh, we are using a supervised algorithm, right? Now we know what this means, right? Meaning supervised algorithm, meaning we train the algorithm and then, and predict on new data. So that's it, all right? There's a new kind of algorithm that starts coming around, and this is a kind of bleeding edge, and I want to show you guys a few, just a kind of quick things called reinforcement learning, just so you're aware of what's coming up. So it's basically reinforcement learning is kind of how you sort of train a dog, right? Kind of like imagine you want to teach your dog to sort of say sit down or do a trick. What you do is when the dog does what you tell him to do, you give him like a treat. You are reinforcing, right? You're kind of rewarding the performance, right? So people said, hey, why don't we try this with computers, right? Why don't we reinforce good behavior and the computer can learn to solve complex problems, right? So the kind of the way is like, imagine you're kind of teaching a robot to navigate a maze, right? So what you do is you sort of set up these rewards and penalties. So reward is something like, if you find a cupcake, you get 10 points. But if you step into a fire, you lose 10 points. So I'm penalizing, right? And if you find the ice cream, you get 20 points. So what I'm doing is I'm not telling robo right or wrong. I'm sort of doing like a point system, right? So I'm telling robo, okay, hey, if you can navigate the maze successfully, you win. But if you sort of get stuck in a dead end, you lose. So I'm sort of gamifying the learning. So the robo eventually kind of figures out what's the best way to do this. So like for example, if imagine you're training a dog, and as soon as the dog figures out, if he does what you're saying, he's going to get a treat. So he'll kind of follow your commands. Same thing, right? So kind of a crude example, but very relevant. So let me show you guys this. So it's called reinforcement learning, and there's a lot of research going into this. So it's something to sort of look forward to. Let me show you guys some of the advances that's happening, right? So right now, a lot of people are doing this for playing games, teaching them how to play games. So this is a popular game, right? It's called Breakout. It's a popular arcade game. So what they did was they asked the algorithm to learn this game. They did not tell the computer anything about the rules. They said, here, it's like, you bring a new game home and giving it to the kids and say, here's a new game, go figure it out. You're not teaching them how to play the game, right? So now the algorithm has been trying this game for 10 minutes and it's kind of sloppy, right? It really hasn't figured out. Anyway, you guys know this game probably, right? I mean, I spent enough quarters in an arcade playing this game, right? So the idea is you move the paddle at the bottom, right? You see the paddle at the bottom, you hit the ball and you break the bricks, right? So that's right. Yeah, I'm guessing most of us here are old enough to be into arcades, right? Yeah. So as you break the bricks, you win points. So the algorithm was told, okay, hey, increase your points. That's it. That's the instruction. I didn't say anything else. So it's like you imagine, handing your kid this game and say, here's a new game. Figure this out. You want to maximize your points, right? So now the algorithm is kind of playing for only like 10 years. Just 10 minutes. It really hasn't figured it out. It doesn't know what to do, right? It's like imagine you're playing the game for the first time. You don't know, okay, what am I doing here, right? Am I supposed to hit this ball just like a human would? So it's not doing so hot. All right. So remember, this computer was given no instructions, right? Now it's been playing the game for 2 hours, right? It's been at this for 2 hours now. It figured it out. It says, oh yes, I need to move the paddle, hit the ball, and break the bricks. Got it. And then my score goes up. Pretty cool, huh? So this is called reinforcement. So this is playing like a pretty decent human player, but there's more. So now this, the algorithm is playing for 4 hours nonstop, right? And figured out a little trick. So the advanced play on this game is, guys, like, if you break the bricks from this side, yeah, you get the points. But the advanced play is you sort of, keep hitting in the same spot over and over again, and sort of, build a tunnel and send the ball to the other side of the wall. And if you did that, then you start breaking the red bricks, and then your points go through the roof, right? So that's kind of advanced level play. Now, this computer, without having anybody told it, just figured it out just by playing the game over and over again millions of times. So watch this. It's going to build a tunnel, right? So you see right here, it's going to try to build a tunnel right here. See where the mouse is pointing? Watch that. There you go. See that, right? And see the score. So when they send the ball to the other side, it's breaking breaking the red bricks, and those have the highest score. Pretty neat, right? So what's happening here is computers, just by playing the game over and over. You could have played the game like millions of times, right? It figures out the rules, and it figures out how to play the game, like a human. Pretty neat, right? So this is called reinforcement learning. Why is it called reinforcement learning? I'm not telling computer the rules. I'm just rewarding the computer for good, for lack of a better word, good behavior. All right? Yeah. So this is a very cutting edge research happening right now, and we'll sort of see some really cool stuff coming out of this. And right now there's a lot of focus on playing games because, that's kind of, interesting and, gets a lot of press. But the learning method they use are very generic. Let me show you guys one more thing real quick, and then, we'll, let me see if I can do this here. Yeah. This one, or maybe this one.
Dear fellow scholar.
Right, I'll turn off the sound here. So I'll just sit through the video real quick. So again, so this is called computer learning to play hide and seek. So what they're done is they set up a like a playground, right? There's a blue team and red team, and the idea is play hide and seek. Okay, so here's what so far what's been happening is, right? Blue team hides, red team finds, and the blue team has been losing, right? So what they're doing now is they're figuring out, oh, hey, what, if I block the entrance with these blocks and then hide in the room, then nobody can find me, right? So watch this, right? So now, red team can find them, right? Good. So red team wins. So now the blue team is going to figure out, hey, I need to block the entrances, right? So they're still trying to figure out, what do I do with the block? And eventually they figure out, hey, what, I can use the block to block the entrances. Can I watch this? Yeah. There you go. All right. So now they block the entrances. Now red team cannot get in. So now blue team wins. Pretty cool, right? So, and they learn this automatically just by playing the game over and over and over again. All right. Let me show you guys one more cool thing, right? So they are blocking the entrance, right? Good. So now the red team is losing all the time. So now the red team has figured out, okay, how do we win this game, right? So let me show you guys, fast forward a little bit here. There you go, it's coming up next, right? Now the red team says, okay, I need to find a way to get into the room. And they notice this like a little ramp, right? And what they're going to do is they're going to move the ramp next to the room. You'll sort of see this, right? I'll let you guys watch this. There you go. Now, right? They can climb on the ramp and jump into the room, and they say, I see you. So again, pretty cool, right? So again, the robots kind of figure out these are blocking, and the other guys are moving the ramp and then jumping into the room. Okay. So now the blue team gets even craftier. They say, okay, they're saying the red team is using the ramp to jump into the room. So now what we're going to do is we're going to move the ramp inside the room and then block the entrance. Right, you can sort of see how the blue team is moving the ramp in, right? So now the red team has no way of jumping into the room. Anyway, so if you look at this, you say, oh, this is pretty trivial. It's like playing hide and seek, like like kids. But here, a computer is learning this on its own, just by nobody's telling it what to do. We just let the computers play this game over and over again, and they eventually they figure out, okay, how to win the game. Pretty neat, right? So anyway, so this is called reinforcement learning. And this is the cutting edge of research kind of happening right now. And keep an eye on this one. You'll start seeing some pretty neat advancements in this area in the next few years. Anywho, so that's that. All right. All right, guys. So that's basically algorithm summary, right? Basically, we have supervised, unsupervised, and the latest one right now is reinforcement learning. Just to kind of give you a taste of what's coming up. By the way, this is another cool thing. So this is a computer generated art that is sold at 400,000 in an auction, right? So if you go to this website, obviousart.com, so what they have done is they shown the algorithms, bunch of classic. Let me see, where's the gallery? There we go, right? One of the classic arts, right? And then the computer basically learns from looking at all the arts and kind of creates its own drawings. I don't paint, I should say. And one of these paintings is sold for 400,000 in an auction. Anyway, so right. So the AI algorithms are doing more than just crunching numbers, right? They're doing some pretty cool stuff here too. So, all right, guys. So with that, what I want to do is some of the algorithms. I want to quickly talk about doing AI projects because I know that's a lot of interest to you, most of you here. Okay. So now we sort of did a tour of what's state of the art, what are the algorithms, what are use cases. So let's step back and say, okay, how do we use AI in my company? So before this, I always say we have to have a realistic expectation of what kind of problems AI can be solved, right? And this is a kind of it's a very simple question. It's not a very easy question to answer. The one I really like best is Andrew Ng's question. It's basically a 1 second rule. So what he said was, if a human can do a task with less than 1 second of thinking, right? Currently, we can do that with AI. So if you think of a task that that takes you less than 1 second to execute, right? 1 second of analysis. Our current artificial AI systems can do that for you. Examples, right? So for example, let's say you're looking at an email, you're trying to figure out if the email spam or not. Sure, right? Takes like less than a second, right, to examine, right? Translating sentences, translation from one language to another language. If I show a picture of an image, whether you can tell me if it's a car or a cat or a boat or a house, right? So same thing, like for example, if you're like, let's say you have an AI system monitoring your assembly line, and you want the assembly line to pick out AI system to pick out products that are damaged. Right, let's say here's a screen cracked, so you want to sort of remove it from the assembly line. Right, again, takes less than 1 second thought. AI can do it. If you're customer support, right, you want AI to examine your tickets and kind of either automatically try to answer your ticket, or maybe even send it to the right queue. Right, so for example, let's say I'm applying for a mortgage, and I'm sending a ticket, so maybe that goes to the mortgage department. Right, so. And also, things like identifying cancer cells and all. Anyway, so all these things AI can do now. Again, it's kind of the 1 second. Again, it's a little fuzzy, right? But I think this is a pretty neat way of looking at this. So we need to have a realistic expectation of what can we solve with AI. So, and on the same thing, AI cannot do, right? It cannot do complex tasks that combines multiple skills. So for example, if I ask one of you guys and say, okay, can you write a research report on stock market today? Right? So it involves looking at the stock market, understanding the trends, and reasoning and writing a report. Those things AI cannot do just yet, at least not well, right? So, and also if you don't have enough data, AI cannot help you much. And this is the problem in my current project we are going through. We are trying to do a image algorithm, but we just don't have enough data. And the customer is basically, they're now going back to, their factory floor and collecting more data, right? So if you don't have enough data, there's not a whole lot you can do with AI. You remember the equation, right? AIs do well if you have sufficient data to train them, right? And another thing, AI is going to do well is it's called intention. Intention is like, like let's say they see a picture of a traffic warden, right? They're kind of saying, okay, hey, what is it saying? Is it saying like stop, or is it kind of waving me to come forward, right? So those things are kind of hard to do right now. Again, these are called understanding human intention, right? It's not exactly doable with AI. So there are a few things AI can do really well, like sort of the examples I've shown you here. So if you have problems like this, great, right? AI is can deliver it for you. But you have some of the complex tasks that takes like has to do a lot of steps. Right now, AI is not a great fit. And also, if you don't have enough data, it's kind of a tough start as well. Okay. So again, sort of, when you're thinking about some of the project, after the class, you're wondering, okay, so, okay, cool, I cannot get the AI, I get the buzz, I get the technology, what can I do? We recommend you guys think about tasks, not like workflow, right? And this is a failure I see a lot of the time. People try to say, okay, hey, I have this workflow, let me do the whole thing with AI. Usually doesn't work out that way. So what we recommend is identify certain tasks in the workflow, right? Like for example, let's say your customer support, tickets are coming in. Maybe your AI is not smart enough to answer the tickets, but maybe it can do some basic sorting of tickets, right? So when a customer sends, hey, I can log into the website, maybe that's, that ticket should be sent to the tech support team. Or if the customer says, oh, my check bounced, right, or something, then maybe it has to go to a different department, right? So it can do that for you, meaning routing the ticket, answering the ticket, maybe or maybe not, right? So I always recommend my clients figure out tasks that AI can do for you, right? So the customer ticket. So routing tickets is much easier than kind of, right, than kind of actually trying to answer the ticket. So always think about that, tasks, not entire workflows, right? And also, and this is another thing, I always ask our customer, this is a current project, we are kind of stuck on is, we don't have enough data. They want to use AI, they want to use a cutting edge AI algorithm, but they just don't have enough data to train the AI algorithm. So we kind of ask them to go back and gather some more data because there's no other way to proceed, right? So for example, let's say you want to deploy AI on your assembly line to pick out damaged products. What you need is you need to have some pictures of damaged products to train the AI, right? You train the AI, hey, this is damaged, right? Maybe there's a this is like a screen is off or something, right? Maybe there's a crooked, something crooked or something's popping out. Those images you need to tell the AI, yeah, these are all damaged goods, right? Yeah. So make sure you have enough data. And also, for example, I show an example how an AI system can look at an MRI image and quickly predict if this patient has tumor or not. So sometimes I get a feedback saying, okay, is it going to make doctors obsolete, right? So not necessarily. Here's why, right? Because like if you're an oncologist, right, you spend quite a bit of time on your day looking through pictures and evaluating pictures and saying if this patient has cancer or not, right? But a trained oncologist, they do a lot of other things, right? They consult with patients, they perform surgeries, they train interns, right? So maybe you can deploy AI to kind of ease their work in examining images. So maybe they don't have to spend 3 hours a day looking at thousands of images. They can let the AI system evaluate, and then maybe AI system can flag only the images that it's not sure about. So you're kind of removing the burden a little bit. You're making them more efficient. But this is what I always say, right? So we always say AI can sort of do the sort of the grudging work, right? So the grunt work, and then focus on sort of free people to do more like higher order functions, right? An oncologist things like interacting with patients, right? Performing surgeries, right? Let them focus on this, so they don't have to spend their day kind of spending hours reviewing pictures. Right? AI can do that for it pretty effectively. So we'd always think like that. Again, not the entire not the entire workflow, but particular tasks, right? So, all right, guys. So here, and I kind of I want you guys to think about this a little bit here, right? So here's like a little template I ask and say, okay, you want to do an AI project, right? So I always think about to start the project, you need some data. Right? So I always think about what do we already have? Do we have data? If you already have data, that's great. Right? That's the best case scenario. Or maybe we should start collecting this data. Things like, let's say you are trying to analyze some website traffic or something. Maybe you're not recording your website traffic. Maybe you should start collecting, right? So that's a good start. Or maybe you can get some, buy data or get data for free or, right, from other data sources. For example, let's say you want stock market data. You can probably buy it from a lot of vendors. You want some, US census data that you can probably download from, from a government website, right? So start with this, right? Start thinking about saying, okay, what data do I have? If I don't have it, how do I get it? Yeah. All right, guys. So very quickly, and this is sort of the last section, right? What do you need? So let's say you're like, you know what, yes, you're just, you're like, yeah, we should do a project. So what do we need? I always say, right, step number 0 is you need to make sure you have enough budget, right? Because this is going to take some effort, right? And the next thing is identifying a problem to solve. So it could be something like, okay, we want to increase conversion on our website, or we want to answer our customer tickets, in under 10 minutes, something like that, right? And then step 2 is making sure we have enough data. Right? We talked about this quite a bit, right? And then also, thing is, we need the right people to do this. And let me talk about this a little bit here because, this, I get a lot of questions on this one all the time. So it's called building an AI team. And most of you here are managers. You manage teams and run companies, and this is not an easy task. Building an AI team, right? Because there's basically an arms race of hiring, machine learning and data scientists, machine learning engineering data scientists, and they're very expensive to hire, and also keeping them is also kind of a difficult task, right? So working with a lot of our clients, what we realized is upskilling your team works really, really well. What do I mean by that is, like, let's say you already have a team in place. They know your business, they know your process. Give them tools and techniques. So teach them or train them so they can actually apply the new tools and techniques to the problem. Because if you think about this, AI is not a product; it's an enabler. It's just a new tools and techniques, right? Just like, let's say you have a team that does analytics. They use R or Python or SAS or anything, right? So that's their tool set. Teach them AI, so now they have another tool in their chest, so they can actually solve the problem. And I'm really big on this because your existing team, they know your business, right? They know what problem you face, and also basically, you have a history with them, right? Who's the performers, who does, what's the strong points, everything, right? So you always tell them, try to sort of train them, right, before you sort of go and hire an entire team. And sometimes you do have to hire. And when we hire, this is what we say, do like what we call impact hiring. What I mean by that is, like, let's say you need like a 5-person team to work on the new project. So rather than going and hiring 5 people outside, from outside the company, what we recommend is, like, maybe hire like one senior person who's like a data scientist or machine learning engineer, and make them as a team lead. And then maybe you can sort of upskill the rest of the team, right? So if you need 5, hire 1, upskill 4. And this formula kind of worked for us really well and for our clients, because, like I said, right, sometimes you need outside expertise. There's no other way around this. But hiring the entire team from outside sometimes can be very prohibitive. And I know our clients spend like 6 to months to 12 months just trying to hire a team, right? It's much easier and a lot less kind of expensive to upskill your team. And again, so your scenario might be different, and if you have any questions, I'm happy to answer this. You can shoot me an email. You have my contact. I can share some of the tips. We have sort of work with our clients, right? But yeah, basically, we can talk about this for like an hour, but I just wanted to give you some quick pointers. So summary is, try upskilling or try impact hiring, meaning like if you need 5, hire 1, train 4, right? So I'm happy to talk about this, if you have more questions. Now, so okay, you got the project, you got the people. So now the thing is, okay, so how do we do this? Like sort of the nuts and bolts, right? Basic choices, like right now, just like any other software, it used to be called buy or build, right? Either you buy a commercial software or you build it yourself. Now there's one more thing in the mix: buy, rent, or build. So let me talk about this. So buy is pretty straightforward. Like buy is like, let's say you have a certain problem, and there's a commercial solution that that does this for you, right? So maybe you're better off buying this commercial solution, right? So let me ask you guys this: what sort of the pros and cons of this approach? So let's say there's a commercial solution available. You can just get that. Can you guys maybe maybe type in the chat window a little bit? What do you think? Sort of the pros and cons of buying a commercial solution for your problem. What do you guys think?
So for us, because this is something that a couple of departments that I work at in Veterans Affairs are discussing, for all of these solutions, the problem is that many times our leadership and even our staff don't know what to purchase, or they don't know how to write contracts, or they don't know what services they need. Like they don't know how to structure a project around this. So it doesn't matter if you have a lot of resources, or if you understand your problem well or not. Most times we don't have the expertise to know which of these things to pick and how to go about it.
That's right. That's a good point, actually. Like for example, yeah, if you sort of having a, right, evaluating what's out there, right, and qualifying. Exactly. Yeah, yeah. That's a good point. That's a good point. Yeah, thank you, April. Yeah, yeah. And I see some others coming in as well. So things like, yeah, maybe the commercial solution is not exactly the right fit for you, right? Maybe, they only solve like 70% of your problem, right? And also cost, obviously, right? So some of the commercial solutions, yes, I mean, they can be pretty pricey, right? So these are things you have to evaluate, right? Versus like building something versus buying it. What are the pros and cons, right? So another option, and this is the relatively new option, renting. So this is kind of became popular with cloud companies, right? So in the cloud company, what they do is they provide, AI service, not just cloud companies like Amazon, Google. There are a lot of vendors as well that provide AI service. So maybe rather than building this, you can rent this from them, right? So a classic example is, seen as like, let's say you want to do some image recognition problem, right? You can try to build this on your own, and it's a significant amount of undertaking. However, there are a lot of vendors, even including the cloud vendors, can offer this as a service. Like for example, Google has something called Google Vision, right? So what Google Vision is like, they sort of train, they train on a lot of data. So they turned that into a service. So you upload your picture. Remember the Clarify demo we did yesterday, right? You upload a picture and then it tells you what it sees in the picture, right? Remember in the Clarify demo, you sort of look at upload a picture, it'll say, I see an elephant, I see a river, I see grass. So all that, because they train on so much data, they tend to be very accurate. Same in cloud vendors, like Amazon, for example, they are turning, their algorithms as service as well. So maybe rather than building this from scratch, let's say I'm doing a solution to let's say identify number plates, right? Or read credit card data, or read driver's license. I can just rather than building this problem from scratch, I can just use one of these services, right? So yeah, so again, something worth considering, right? Again, if you think about the same thing, right? You can think about the pros and cons, right? Because these are very easy to get started, but at the same time, you're kind of, it's like paying rent, right? You're kind of, the more you use, the more you pay, right? You don't own anything basically, right? You're kind of renting the service. And some of our clients are using this because for them it works out, right? So again, maybe maybe a choice for you guys as well. Yeah, so right, exactly, yeah. So yeah, so trust me, yeah, competition is very fierce, and I see April's comment here, right? Yeah, there are a lot of vendors. You will get a lot of sales pitches, and part of the reason is like, even evaluating them is not trivial, right? How do you know vendor A is better than vendor B, right? One of the cases I'll tell you is like, one of our clients went with the vendor. We helped them evaluate this. So when we evaluate the service, we kind of said, okay, per month, I'm just making a number up, right? Per month, we expect to pay, like say, 50,000 for this service. But when the bill came out, it's like well north of 100,000 per month. And we're wondering, why is this right? Look, our use case is exactly as we predicted, but why is this, our estimate, like, we estimated 50,000, but, we are kind of paying like 100,000 plus for every month for the service. And as it turns out, there are a lot of these hidden services, right? They will say, oh, there's an extra fee for this, there's an extra thing for the, bandwidth, there's extra for that, right? So when you sort of add up these things, it can be a little surprise. And most of them, I would say some of them, not very forthcoming about the cost, right? So, and sometimes, even, this is an example, we got blindsided because, we thought we did our due diligence, but, hidden costs kind of, right? So yeah, you got to be very careful evaluating this, even though they may seem very like, very easy. Yes, just, oh yeah, just click this button and you're good to go. Yeah, right. You got to keep an eye on the cost as well, right? Because we all have budgets. Right? Anyway, something we recommend this to our clients because because doing this from scratch is a huge undertaking. For example, if you try to do an image service like Clarify, it took them years to build that that level of sophistication for the image algorithm, right? Building this from scratch for us might take months or years. So maybe we don't have the time, or we don't want to do that, right? So yeah. So anyway, again, just like every choice, you have to kind of evaluate this, and like I said, each of this topic we can spend like an hour talking about this, but I'm just giving you some of the highlights, and I see some good discussion points on the in the chat as well. Yeah, yeah. Yeah, great question. So like, how do you protect your IP? That's a great question, right? So for example, this is something a little bit of a tight rope you have to walk. A lot of the vendors will have a very strict data policy, right? Because when you're doing an AI as a service, you're kind of uploading your data to them, right? So let's say I'm using a service to identify driver's license. You're kind of uploading a driver's license to the service, right? And who knows what they do with this? Are they saving it? If they are saving it in local, in the local, like how long are they saving it, right? There are a lot of things you have to kind of, and a lot of these things have to come part of the contract, in your SLA, right? Yeah, and then you're kind of trusting them a little bit, right? So let's say I'm doing a Google Vision to, understand my driver's license, and I'm updating my client's driver's license license images, right? How do I know, they are discarded, or how do I know they're making sure they're not just leaving them around, right? Yeah. So these are things we have to really think about. Absolutely. Yeah. Mm-hmm. Exactly. Like April, you're saying, yeah, like the data you have is so sensitive, right? So you really need to sort of, and usually what we do is like we make it part of the contract, as in like, hey, like this is the SLA, this is the agreement to use the service. Yeah. Yeah. And some of them will have specialized provisions, like for like government data, health data, things like that. So like I know Amazon has an entire division that does only government consulting, right? And they are completely isolated from the rest of the service, like completely firewalled off, so the data doesn't leak out, right? Yeah. So again, this is something, and you're right. I mean, and so like somebody mentioned, these are not trivial to evaluate. You have to spend a lot of time evaluating and understanding how they practice. Yeah, yeah, that's true. Okay, great, guys. Yeah, so really good discussion. Thank you for that. Yeah. And then final choice is building, right? I mean, this we are familiar with. Like, so we say, what, none of them work for us. So we cannot go and build. Actually, that's the current project we are working on. So the client wanted to want a solution that they can own. So they didn't want to use any AI services because they like again they are concerned about the security and the data, sensitive data, and they didn't want to buy a commercial solution because they wanted an open source solution. So right now we are helping them build a custom solution based on open source software, right? Because that's their mandate. Because they are sort of a I can't get too much into this, but they are sort of a like a kind of like a public agency, kind of they work with a lot of public agencies, so they need to have complete visibility into their software. So they couldn't have any black box kind of a commercial software or service level software at all. Right? So they are building everything from scratch. So maybe that's a restriction you have, right? Yeah. So again, so just evaluate the choices, please. Again, like I said, sometimes the choices are not straightforward. So that's why you guys can evaluate. And one thing I would say, and this is like a little little sales pitch. If you guys need anything like evaluating in your software, we do this all the time, and we're happy to help. Right. So, all right. So that's all the sales pitch there is. All right, guys. One final thing I want to go over. Right, we talked about the workflow process. So I'll skip this, and I'm going to quickly talk about something called some of the experiments gone wrong in AI, and why it happened. Because I've been showing you sort of the good side of the AI, right? But there's the other side to AI as well. Let me show you guys this. Again, by the way, these these are like all reference for you guys. For example, if you want to deploy AI on your mobile, what are your choices, right? So you can sort of see here, right? So I'll give you a list of things like, let's say you're going to use image recognition services. So these are some of the really highly recognized image services that you can see. Here's a Google Cloud Vision, Microsoft has one of their own. Clarify we talked about yesterday, right? So kind of think of like an references place. Yep. All right. So let me skip through to the end. And I want to show you guys AI gone wrong. So this is the last section. Yep. So I want to show you some of the use cases, and and there's a lot of things we can learn from this, and that's why I want to highlight this, right? How some of the things kind of failed. So this is a very popular use case. Like Facebook had 2 chatbots. So they developed the chatbot and then basically sort of hook them up and then let them talk to each other, right? And after a few days, what happened is they realized they were talking to themselves and nobody could understand what they're saying. So basically they invented their own language. So the one bot will say something and the other bot will respond. And this is some of the, right? These are some of the things they're kind of saying, right? And if you read this, like none of them make any sense. so they basically invented their own language. So the researchers couldn't really understand what they're saying. So they basically had to, stop the experiment because they couldn't really understand what's going on, right? So that's a kind of a classic case, right? So AI is kind of basically overtaking, right? And then kind of so we have no visibility into the models, right? And another one is this kind of a classic case. You probably heard about this. So Target had this deployed this algorithm. What they do is they look at what people are buying and then start recommending things for them to buy. So one of the things they did is like they identified top, I think, 25 products. They say if they're both together, they probably guess you're pregnant, and then they sort of start sending you coupons and things like this, right? To more pregnancy stuff. So one of the things that happened was in one of the store, a man wrote and say, "Why are you sending this pregnancy stuff to my daughter? Right? She's just a teenager, right?" And so the manager said, "Oh, we are sorry. We'll take you off the list and all this." And later we found out the teenage girl was indeed pregnant, right? So she was going to Target and buying, right, pregnancy-related things, and the algorithm was right in this case. But they kind of, how do you say? This is like example of sometime you got to be a little sensitive, right, when you deploy the solutions, right? Because like I said, hey, right, yeah, the daughter was actually pregnant, but just like there's a, you got to be, you can be tact, right? You got to be a little tactful when you're doing these things, right? So AI is right, but kind of insensitive, right? So that's another use case that I didn't really, they didn't really think this through. Here's a kind of a Tesla self-driving, right? So this is a big field right now. So one of the things that I realized is, so you can see the car, right? The top of the car is just sheared off. How did this happen? So what happened was, as the car was driving in a rural road, one of the truck was backing out. So the car saw this truck, and he'd never seen a truck like this before, right? Sort of this side of the truck. So car didn't, car just said, it's just empty space. So he decided to drive through it. so you can see, right? It's like, so you can imagine the car just driving under the truck. So the top is completely sheared off, right? Why? Because the truck, so the vision system in the self-driving car didn't really understand. Oh, okay, I'm just looking at like an empty sort of white space. So, right, so there are some of these things kind of, right? Some of those things kind of, because why? Because the car was never trained on a data like this. It never seen the data, so it didn't really understand it. Yeah, so, right? So self-driving car. And here's a classic one. So this is another one. So they deployed an algorithm, a camera with an algorithm to identify wolves, right? So what happened was, in the summer months, the algorithm did really well identifying the wolves, right? It'll sort of allow the farmer, so they don't kind of go and eat the livestock or whatnot, right? But then what happened is when the winter came in, it started basically identifying everything as wolves. So even when you see the picture of a dog, when the camera sees the picture of a dog, it'll send an alert to the farmer and say, hey, there's a wolf in the property. And they wondered, okay, what's going on? Why did the algorithm that worked really great in summer now started misbehaving in winter, right? So as I start digging into it, so here's a picture of a picture of a dog, right? And the algorithm, basically said this is a wolf. And the researcher went and said, okay, why do you think this is a wolf? Explain this to me. And the algorithm now highlighted what it is considering as important part of the image So it thinks it's a wolf. Can you guys think what's the important part of the image? It's not the dog. It's the snow. Exactly, right? So as you can imagine, like, so the training images they used for wolves, right? So wolves tend to be more prone in winter. So a lot of the wolf pictures had snow in the background. So as they trained the algorithm kind of said, interesting. If I see snow, it's got to be a wolf. So it didn't even pay attention to the actual animal's face, right? Because again, like I said, the algorithm was kind of right because it kind of assumed all the wolf pictures have snow. So if I see a snow, I'm going to assume this is a wolf, right? I don't even care what the animal looks like. So only when they start debugging the algorithm, they realize, oh wow, it's not even looking at the animal picture; it's just looking at the background, which is snow. Interesting, right? So again, the algorithm is trained on the data, and this is why the data has to be correct. Because if you feed wrong data, or if you feed sort of monolithic data, you get monolithic results. Right? Again, so all this, you can see watch the presentation on the video and all of this. And this is another classic one. So Amazon said, hey, we need to hire a lot of people, and we get a lot of resumes. We are going to use AI to shortlist the resumes. So what they did was they basically fed the algorithm on the resumes of everyone, the current employees. They said, these are the employees we actually interviewed and spent a lot of time interviewing and hired. We want more people like this. Right? Makes sense, right? If you're a company, you already have good people working for you. You sort of feed their resumes and then say, all right, algorithm, go find out more people that looks like the people who work for me. And the algorithm started doing this, and what happened was the algorithm started choosing, shortlisting, basically male applicants. Can you guys maybe guess why? Right? So right now, if you think about this, it's pretty obvious. You're like, obviously, right? Because in the tech field, majority of the employees tend to be male, right? Especially technical, right? Engineers kind of position, right? Software engineers and data scientists tend to be male. So if that's all the resumes you get, let's say in your resume, let's say in your company like 70% men, and you even the algorithm resumes of your workforce, and 70% of the algorithms, the resumes, are male resumes. Right? So the algorithm is implicitly picking up a pattern, saying, maybe algorithm realize, maybe Amazon is preferring males. You didn't realize, right? Because looking at the resumes, that's what they figured out. Right? So as soon as they discover this, they stop this process, and then so I think what they are doing right now is they are training the algorithm on the balanced data set, right? Meaning equal male, female resume, so that that's not that's not an issue. So this is a classic case of algorithm kind of learning from the data it's given, but picking up some bias we didn't even realize we had. But the algorithms are so good at picking up the bias, right? So anyway, so this is remember, have you guys heard the phrase garbage in, garbage out? Same thing, right? AI is only good as the data you train on. If you feed it bad data, or kind of monolithic data, like like here, like the snow and the wolf, right? That's what algorithm is going to pick up. All right, guys. So I thought I would sort of stop here, just right, because we want to show you the sort of the other side of the AI too, right? So look at these use cases, and I sort of provided links for you guys to kind of go and study if you're really curious about some of these cases. But yeah, right. So anyway, summary. So here's the summary, guys. What have we done is we looked at AI as a technology, use cases. We looked at algorithms, state of the art, like things like reinforcement learning, and we also looked at things like how do we go about deploying AI, right? And we looked at the impact of data. Right, and even more here, data is more important. You can sort of see here, right, how important data is, in tweaking the algorithm. If you feed the wrong data, you get the wrong algorithm, right? So data is hugely important, and we talked about things like how to do big data, doing things on premise, in the cloud. So we covered a lot of topics, and we are pretty much at the end of the class. So I think it's a good place to stop here. But if you have any questions, you can hang around. I'm happy to answer any questions you guys might have. But otherwise, we are done for today. Again, thank you so much for being in the class. I know it's not easy taking time off, so I really thank you. And guys, if you need to stay networked, please punch in your details here. We'd love to stay in touch with you guys. And my details are here as well. Right, you can shoot me an email. Find me on LinkedIn. I love to stay connected. And if you have any questions, you can send me an email anytime. I'm happy to answer. All right, guys, so let me stop here. Thank you so much. But if you have any questions, please feel free to hang around. I'm happy to talk to you guys and answer any questions. Very good, guys. So if there's no other questions, again, I'll send you guys an email with all the links and everything. So look for the email. I hope to stay connected with you guys. Thank you so much. Let me end the meeting right now, and I'll send you guys an email all later. Okay, thank you, guys.